Aloha, Richard Halverson here. This is ICS211. And today I'm going to, in this recording, I'm going to go over searching the short chapter on searching and algorithm analysis. So let me share my screen. And I'm going to cover these sections 1, 2, 4, and 5. And I'm going to leave section 17.3 for a second video on the lab. My idea here is that you should be able to do all these labs on your own, and you only have to look at the video when you're stuck. So let's just start here. Okay, so we're talking about searching, and searching means you have an array and you're searching for a particular element in the array, and we are assuming that indexing is the most efficient way to access elements in this array. So it's either a regular array or array list, but it wouldn't be like a linked list. So there's two types of searches. There's linear search and there's binary search. Linear search does not assume that the array is in order. Linear search can be used with any old array in any old order, okay? And of course, the way a linear search works is it just starts at the beginning. Let's say you're looking for, so you should click through these, but let's say you're looking for 14. It's going to start at the beginning and it's going to go all the way down the line until it finds 14. And then when it finds it, it's done. And what in this particular type of search, it would return the index, and then presumably with that index, you could access any other properties or whatever having to do with this element. And so that's a linear search, and this is what the linear search algorithm looks like. Here we're declaring an array. See, this is the linear search algorithm. Okay, it starts here. We're going to have a scanner. We have an array of numbers that happen to be in order, but they don't need to be in order. This is linear search, right? And then here we're printing them out. This is what the array looks like. And then enter a value that you want to look for. Enter a value, and then it does a linear search. This is the array. This is the value you're looking for, the key value that you're looking for, and it returns the index. And then it says it displays it out. Either it was found or it was not found. So here we're looking for 10, and it returns 3. And so the linear search algorithm here goes through, starts at the beginning, loops all the way through until it finds the key. And once it finds the key, it returns the key that it found. If it makes it all the way to the end, that means it didn't find it, and it returns a -1. So that's how the linear search works. This talks about, make sure you understand this concept of runtime is how long it takes to execute, and it usually depends how long does it take to execute based on the number of elements in the array, or how big you're looking at the size of the data. And so we're going to learn more. We're going to be more concerned about that when we talk about algorithm analysis. Anyway, so the next section here, binary search, it's a little different. It assumes a sorted array. It assumes the array is sorted. It assumes that if, for example, if you look in the middle, you find a value, the sorted value, and if the thing you're looking for is greater than the middle, then you know it's going to be in the top half. If the thing you're looking for is less than the middle, then you know you're looking at the bottom half. So with each look, you can cut off, you eliminate half half the remaining elements to look at, and that's the beauty of the binary search. So if you have a very large list, they all have to be sorted. To actually find the element that you're looking for doesn't take as much time as you'd think, because each time you do a look, each time you do a comparison, you're eliminating half the list. And if you think about it exponentially, if you have a list of 1,000, each time you look, it's going to be it's going to be first 1,000, then 500, then 250, then 125, then 60, 62, then 30, then 31, then 15, and then you see very quickly it goes down to the number that you have to look through to find the index, or to find the value that you're looking for. So anyway, this demonstrates that. You click through these. You should click through all these because you get all the points. It just shows that you've gone through it and you thoroughly understand what's going on. So you click through this and you see this animation here. You can see it's each time it splits it in half, and each time it determines if it either found it or it's above or below. If it's above, it resets the bottom half and finds the new middle index. And once, so here it found it. If you keep looking and the end index is crossed, then you know that it's not in the list. So let's just go through this one more time. Okay, so we're looking for 16, and so we calculate the middle, and then we determine if 16 is greater than the middle or less than the middle. In this case, it's greater than the middle, so you know it's in the top half. So then you move the low up to here, and now you calculate a new middle, and you basically do the same thing again each time on half the list you were looking at, and eventually you either find it or you determine that it's not in the list. And so this is the binary search algorithm, and again we come in with a list with an array of integers. In this case, it has to be sorted, and then a key that you're looking for, and we have these three variables here: low, middle, and high. And so we start out where low is 0, and high is the very top of the array, and high and low are going to change based on whether or not the middle is determined, if the middle is less than the key or greater than the key. And so first we calculate the middle. We take the high plus low, divide by 2. And if the number at the middle is less than the key, then we're gonna move the low end up just past the middle. If the number at the middle is greater than the key, then we're going to move the high point down to the middle. Let's see, is this right? The middle. If the middle is greater than the key, yes. So that means the middle is above the key, so that means the key is going to be in the lower half. So the high pointer is moved to just one less than the middle. And this keeps on looping. Low is being increased or high is being decreased. It keeps on going until eventually you either find the one you're looking for. It's neither lower or higher, but it is exactly the one you're looking for, or high becomes lower than low, or low becomes higher than high. So in other words, they've crossed, and then you know it's not there. And that's what happens when this is no longer true. end up returning -1. Okay, so that's how binary search works. Go through this and make sure you understand how it works. Go through this, and you can see here we're talking about how long it takes for binary search to run, and we recognize that it's log to the base 2 of the number of elements in the array, because each time it gets cut in half. So if there's 1,000 elements, it's only going to take 10 tries, or 1,024 elements. It's only going to take 10 tries before you either find the element or you determine that it's not in there. If it's 16,384 elements, then it's going to take 16 tries, 14 tries. Anyway, so go through that, make sure you understand it. This binary search lab, I'm gonna wait until I'm gonna do this in a different video just after this video. I just want to get through these sections here, because this is like the lecture. This is kind of the stuff you're responsible for. The labs, you should try to do those on your own. If you can't, then you can watch the video. All right, so this talks about big O notation, and it's a way of describing how a function behaves in relation to the size of the input. So we basically figure out what it's loops. It's loops based that grow with the size of the data, or loops within loops that grow within the size of the data, and you come up with an equation, and then you're only concerned about the highest term. So this goes through and explains how you figure out what the big O value is, and it's not difficult at all. Okay, but if I try to explain it to you right now, it's just going to be confusing. So I think you should go through this. But what we computer scientists do is we learn about these big O functions for our algorithms. And the linear search algorithm, for example, is O of n. They say it's O of n because if it's got 100 items, it'll take on the order of 100 worst case comparisons. If it's 1,000, it's going to be 1,000 comparisons, and so on. So it grows linearly with the size of the array. For a binary search, it's log n, because for the binary search, if it doubles, it only takes one more. Doubles again, it only takes one more. See, so that's a much preferred O of n. It's shorter. For sorting, our sorting algorithms that we're going to learn in the next chapter are either O of n or n log n. And this compares the growth rates for these different sizes, and in the sorting comparison lab number 3, we will actually compare an O of n squared sort with the n log n sort, and we will compare, we'll count comparisons as the size of the array grows, and we will actually see growth on the order of this versus growth on the order of this. And you can see n squared grows much faster. I mean, it's 2.7 hours here. Here it's still seconds. Milliseconds, 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 seconds. This is milliseconds, 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 seconds, 100 seconds, hours. So you see the growth is much more dramatic here as these numbers get bigger. And so this is what computational complexity is all about. It's finding an algorithm that's here and seeing if you can figure out a new way to do it where it's here, or finding an algorithm that's here and figuring out if there's some other way to do something where we can get it down, one more order. So this is example algorithms. This is binary search right here. O of n is linear search. Merge sort is O of n log n. Selection sort is O of n squared. And figuring out the Fibonacci, a Fibonacci number is exponential. It looks like that. All right, that's O notation. What's next? Algorithmic analysis. Here we talk about how there's worst case and average case, and of course there's best case also. Those do matter for a sort like insertion sort. The best case is much different than the worst case, but for selection sort there's not so much difference in best case and worst case, and so you learn that. And this talks about how you can actually figure out, and by looking at the code, how you figure out the worst case time, analyzing how the loops work and all that. So there's no challenge activities in this chapter. There's only the lab, and so make sure you go through and understand all this. This is the only way I know that you examine this stuff. This is important stuff. This is in the learning outcomes, the course learning outcomes. You should learn this. And the only way I know is that you've clicked off these participation activities. And so make sure you do that. And thanks for watching.